We're back. Let's talk about pH. pH is something that you know of, you've heard of, and you probably know a little bit about the scale and what a particular value might communicate. First thing I want to do is kind of remind you of that scale. On the pH scale, we have a neutral position at 7. Pure water would have a pH of 7. There are no units on the pH scale. At the bottom end of the scale, between 0 and 7, we have acids, okay? All types of different acids. Generally, the stronger the acid is and the more concentrated the acid is, the lower the pH is going to be. So if I look at something like battery acid, that is sulfuric acid. It is a strong acid. It has a very low pH. pHs can even drop if the acid is concentrated enough and strong enough. pHs can actually drop below 0 and provide a negative pH. It's possible for that to happen. pHs above 7 are considered to be basic, and these would be things like hydroxides. So if you look at the end of this scale, Li is essentially sodium hydroxide. And when it is concentrated, it's going to have a very high pH. The only other thing I want you to know about this scale is that, kind of like earthquakes, there is a huge difference between each point on the scale. So if I look at an acid with a pH of 2 versus an acid that has a pH of 3, they're 1 unit apart on the pH scale, but that's actually a difference of times 10 in acidity. So a pH of 2 is 10 times more acidic than a pH of 3. And if I go from, say, a comparison of 2 to 3 to a comparison this time from, let's say, 2 to 4, that is a difference of 2 pH units. It's actually 100 times. Okay. So there are big differences between points on the pH scale. What you may not know is how pH is actually defined and how you go about calculating it. pH has a very simple definition. For our acids and bases, we know that if we put them into water, according to a Bronsted-Lowry model, an H plus is donated from the acid to water to form what's known as the hydronium ion. Hydronium is H3O plus. The pH scale is 100% based on the hydronium ion, how much hydronium is in solution. Okay. And so let's say we have an acid that produces, I don't know, 0.300 molar H3O plus. And I asked you to find the pH of that particular solution. The definition of pH is the negative log of the concentration of H3O plus. So in this particular case, I would say the negative log of 0.300 molar. And so if I plug that into my calculator, I get a pH of 0.52. That's a very acidic solution right there. Let's talk about logs a little bit. I know you've seen them in math class, but let's say that I had a solution that wasn't this concentrated in H3O plus, but let's say I had a solution where the H3O plus concentration was 1 times 10 to the minus 9 molar. Would you know how to find that particular pH? According to this, we would take the negative log of 1 times 10 to the minus 9 in order to find the pH. Taking the log is all about looking at this exponent right here. And so the pH of this is 9, right? There are other scales that are lesser known scales than the pH scale. An example would be the Poh scale. It's essentially the same sort of scale, but based on hydroxide ion concentration. So let's say I have a base, and that base is XOH, and I put it into water. Usually we don't show water, and it produces X plus and OH minus. And let's say that this produces 1 times 10 to the minus 4 molar OH minus. Just making that up. If I wanted to find the POH in this particular case, I take the negative log of that OH minus or hydroxide ion concentration, 1 times 10 to the minus 4, and the POH is equal to 4. Now, there is a really handy tool that relates the pH and the POH scale. It comes from a particular equation you had to write in yesterday's Poh called the Autoionization of Water. We're not going to go into the background today, but this tool right here, pH plus POH equals 14, is really handy. It allows you to convert between each scale. So if I have a POH of 4, like I just calculated, then that tells me that that same solution would have a pH equal to 14 minus the POH 4, or a pH of 10. Okay? So a solution that has a very low pH, POH, has a high pH, and vice versa. Let's look at one other thing before we finish up this video. What if you were given the pH of a solution, but asked to work backwards to find the concentration of a given ion? Let's say I have a pH of 5.2, and I want to find the H3O plus concentration. All I have to do in order to find it is say 10 to the negative pH. Now, putting that into your calculator, we would get 10 raised to the negative 5.2, and we get 6.31 times 10 to the minus 6 molar. And that is the pH of that particular solution. You can do the same exact thing with POH in order to find the OH minus concentration. And finally, you can find another helpful tool. Again, it comes from what's called the autoionization of water. If I take water and react it with water, it can produce H3O plus and OH minus. The K value, or the equilibrium for this particular reaction, since these are pure liquids and are left out of the equation, is equal to H3O plus times OH minus. And in pure water, that value is well known. It's It's called Kw, and Kw has a value of 1 times 10 to the minus 14. The reason we bring it up here is because I can use this equation in order to toggle between concentrations of hydronium and concentrations of hydroxide. Okay, let's come back together and we'll do a bit of practice on this topic.